All right, I want to begin a series of lectures on AC circuits. These would be in addition to my textbook content on this chapter, which is 100% example problems following content that explains all of those equations that you would use in that regard. So I've also uploaded these 5 tab things as individual PDFs that you could download, sent a couple of them in an announcement, and then made another some more after that. So here is a basic AC capacitor circuit, the AC source, and we would describe the voltage, the instantaneous voltage. This would be a peak voltage, and then there's angular frequency, or the frequency of this oscillation, alternating current, and then just a capacitor and the voltage across it would be changing in time, all the sine curves and everything. So let's get at some problem solving here. So in that kind of simple circuit, you have a 0.3 farad capacitor, a microfarad capacitor connected to an AC generator, produce peak voltage of 10 volts. What is the peak current to and from the capacitor if the EMF frequency is 100 hertz? So we have a formula that you would get from the reading, and we would write this reactance as an X value, or we use the capital X because R has already been used for resistor and whatnot. So that's the thing about AC circuits. Remember that there's an impedance, which is all kinds of resistance, including regular resistance, and then the reactance that capacitors and inductors have, because they do impede current flow. So impedance is a more general kind of resistance, covers all the bases. Well, this is a pretty simple formula. It's 1 over omega C. Okay, and so when we now we would need to know that omega, just regular old 2 pi f, that never changes. That's just math land. Okay, and so at 100 hertz, you would just have 2 pi times 100 hertz, and that would give you, kind of the 2 pi, 6.28, 100 times that would be 628.3 radians per second. Okay, so just pure number there. And so knowing that value, we would do the simple calculation, 628.3. You could just say seconds to the minus 1, it's the same thing. It's implied that that's rads per second. And then 0.3 times 10 to the minus 6, because it's microfarads. And that would give you 5,305 ohms of capacitive reactance. All right, so it's important that we realize here this is capacitive reactance. Okay, and so we need that piece of information so that we can subsequently use Ohm's law. So voltage is always, from in a general sense, voltage is current times resistance, just generally speaking, which means in this context, we're going to have voltage across the capacitor will be equal to the current through the capacitor times its capacitive reactance. So we would, we're treating resistance from the old school kind of what's the word I'm looking for? In AC alternating current circuits, reactance is what we thought of resistance in a DC circuit. All right. DC circuits is only that, and now we add this. And so this means that our current would be just that ratio there. So you'd have 10 volts over the 5,305 ohms, and that would give you 1.88 milliamps, because it's going to be times 10 to the minus 3. Your calculator would give you 1.88 times 10 to the minus 3. So that would be our answer. All right, so not hard, but not as straightforward as the DC circuit stuff, because of the difference, because the impedance takes us up a little bit higher viewpoint, and we have 3 kinds of impedance: standard resistance from resistors, but then the resistance that capacitors and inductors have in terms of their reactance value, which we have an X sub C and an X sub L in there. All right. And if you look at the impedance section in any physics textbook, they'll have a formula for Z, for impedance that has resistance, capacitive, and inductive reactance in them. It looks like almost looks like a, well, it is a Pythagorean theorem looking thing, because the way we draw phasors. But that's back to the textbook stuff. All right, so if it's 100, well, you're going to make everything 100 times smaller, and so you could just divide the original thing we had, but just to be explicit, I guess, that doesn't change, but you do have 6.28 times 1,000, okay, inverse seconds, and then that same value, 0.3 times 10 to the minus 6 farads, and oops, didn't want that. And so then we're going to get 5.305 ohms. And since nothing changed, you could just divide 5,305 by 1,000. But if you wanted to see the work, you could certainly see it there. So that's a simple first step into this abyss of solving AC circuits. All right. So I'm keeping my notes here, because I wander, I chase rabbits, and I have to be mindful of that so that these things don't go off in the weeds. All right, so peak current to and from a capacitor is 10 milliamps. What's the peak current if any of these things happen? And so you have, I guess, in general, what we just did, your current through a particular thing like a capacitor would be that formula. That's just Ohm's law business here. And so you're going to have VC over XC, which just means you're really just going to get a 1 over omega C, which means you're going to have omega C VC. That'd be just jamming those equations together as they go. And so if frequency is doubled, all right, then what's that going to work? So our put a I prime, for our doubling, some sort of tick mark on it, would mean we would have these little primed doodads. The capacitance isn't changing and whatnot. And so if I double that frequency, well, then I'm going to have 2 omega and C VC. All right, so we would just write in, you know, uh, that there, and so that's just going to be 2 IC, and we would just have 20 milliamps. So not complicated, should make some sense. EMF meaning electromotive force, that's voltage, that's what's pushing the current. And so if you double that, frequency, it should be unsurprising, at least in this particular capacitive circuit, that you're going to double the current. You're going to push twice as much charge onto the plates. So that would be a kind of a conceptual answer that is validated by the math. Okay. And if the peak voltage is doubled, same thing. I guess I just explained that. I'll call that double prime. So really same answer twice in that one. And if the frequency is halved, well, the EMF is doubled. Okay, and so you bump one up by an amount and then you drop the other one by the same amount, nothing changes. Okay, so current would just stay what it is, and so there's really no need to. You would get the same thing if you plug that in there, but I don't know that we need to write all of that out at your level of mathematics. Better to just know that, think it through, and you could go build a circuit in the FET or any circuit simulator and see that, measure it directly. And I don't think you've had a lab like that, because we're sort of going a little bit past the limit. We're dancing on the edge of what is typical in a course of this size. I think I need to shrink that there. There we go. All right, a 20 nanofarad capacitor. Not a lot of capacitance. Connected across an AC generator that produces a peak voltage of 5 volts. At what frequency F is the peak current? 50 milliamps. Okay, so what do we do here? We have an equation again, just like before, and I'm not going to write it all out since we just did it up top, but we have that in this case, this would be our formula. And omega is 2 pi f, so this is 2 pi f CVC, which means our frequency, whoops, it's not a, there's no, it's not crossover frequency, that's a different frequency. I'm thinking of some stuff coming next, would just be, 1 over that stuff, okay? And so, or it would be rather the IC over all that stuff. So we're connecting these dots here. So we would have our 50 milliamps, and then divided by everything that's not F, so our 2 pi. The capacitance is 20 times 10 to the minus 9 farads, and 5 volts. So right there on the problem. And so our frequency would be about 80,000 or 80 kilohertz. All right. So those of you that are in the circuits course or have had one, you probably got to do something like this, actually build the circuit, either physically or in a simulator. And so this would be this is the math side of it, which I'm sure you did some of that too in that course, and if not, you will. All right, that one. Moving on. A capacitor is connected to a 15 kilohertz oscillator, peak current 65 milliamps, when RMS voltage is 6 volts. What is the capacitance value? And so if we keep using this formula that we've seen. IC is omega CVC. In fact, the textbooks always get to that if you make those substitutions. So that means that C is going to be IC over omega VC. And so we have 65 times 10 to the third amps over 15 times 10 to the third. Oops, I got to put my 2 pi in there because this is a frequency, not an omega. And then, or we could just say properly, hertz, same thing. And then the voltage was 6 volts. So, oh, it's RMS voltage. And hopefully, VRMS, any RMS value is going to be root to the value. All right. So we need a root 2 jammed in there to make this legit. And when you do that, you get 81 nanofarads. So your answer will be 81 times 10 minus 9th. And so the capacitance at this particular setting would mean that you have that much capacitance in a circuit like that. And so why would you need to know to do this is for some reason, these other things are constraints that are somehow on the system, and you need to manage, you need to stay within that lane in a capacitive circuit. This is the capacitor that you need. That's practically speaking, that's what that would be. And this would be one tiny piece of inevitably a much more complicated engineering solution, electrical engineering solution. All right. But it's the little stuff. And then you put all that together and eventually it sorts out. All right. Capacitor has a peak current of 330 microamps when the peak voltage is 250 kilohertz, or at that frequency is 2.2 volts. What is the capacitance value? So again, just sort of rehashing all of this. We're going to have this 2 pi f CV, which means capacitance. So we're really just doing the same thing we did a minute ago. IC over 2 pi f VC. So 330 times 10 to the minus 6 amps over 2 pi, 250 times 10 to the 3 hertz, and 2.2 volts. Crunch all of that together, and you'll get, on your calculator, unless it's in engineering mode, you'll get 9.5 times 10 to the minus 11th on your calculator, which that would be 95 times 10 to the minus 12th farads, or 95 picofarads. Okay, so there you go. If the voltage is held constant, what is the peak current when the frequency is 500 kilohertz? And so if you frequency times 2 is going to mean capacitive reactance over 2. And so if you think back to the formula that we did, I think the very first one we did was XC is 1 over omega C, which is 1 over 2 pi FC. Then you're going to be cutting everything in half. So our answer would mean peak current would double, and you would have 660 microamps instead of 330. All right, so that is kind of the mini lecture on capacitors. And so now, before we move on to inductors, I want to talk about RC filters, which are the main way that this stuff, I guess, is used, practically speaking. So when we can, it's worth saying a thing or two about them because there's some physics involved, but ultimately this is an electrical engineering game. So there are two kinds of filters. There's a low pass and a high pass filter, and they have particular properties. So here with the low pass filter, where the resistance is ahead of the capacitance, all right, this is the thing. So frequencies are less than the crossover frequency and blocks them above it. So hence the filter. These are just terminals for measuring voltage. And then a high pass is switch the order. The resistance follows the capacitance, and you get the exact complementary side there. So there's a lot to say about high and low pass filters. More than that, I'm not going to go there. We'll just solve a few problems and leave it to the specialists to take it farther than that. All right. So a high pass RC filter is connected to an AC source with peak voltage of 10 volts. Peak voltage is 6 volts. What's the resistor voltage? And so, filter meaning we want to filter these things out and these things in. So what are they for? They're for that. I don't think that's complicated at all. So current and voltage of a resistor are always in phase. So again, I'm asking you to remember what you read and or watched in lecture. In resistors, voltage and current are in phase with one another, but capacitor current leads capacitor voltage by 90 degrees, pi over 2. And so, you have capacitors, inductors, and voltage will lead current in one and the opposite in the other. Those are some basic pieces of knowledge. So, but for an RC circuit, voltages are related through this equation, okay, where the square of the peak voltage is going to be equal to the square of the resistor voltage plus the square of the capacitor voltage. Yes, that's a very Pythagorean theorem oriented thing because we imagine it that way in our phasor diagrams because it is that way in terms of its harmonic nature of its function, the oscillating, periodic, sinusoidal, all that stuff ultimately boils down to Pythagoras. A lot of mileage on that. So hopefully we don't need to show lots of math and we can just go straight to that. All right, and so that means we're going to have 10 squared minus the capacitor voltage, which is 6 volts squared. And that means that VR is roughly 8 volts. Probably might even be exactly 8 volts. Yes. Because 100 minus 60, 36 gives you 64 squared. That's 8. Poof. Problem solved. Next problem. So AC circuits are weird. The equations are a little bit more involved, but they're still pre-calculus level stuff when it comes time to solving for them. So low pass RC filter with a crossover frequency of 1000 hertz uses a 100 ohm resistor. What is the capacitor value? All right, here we are again. We're dealing with a frequency here. That's frequency, that's resistance. What's the capacitor value? So we can pull out this equation. So I'm not going to be developing equations. That's textbook stuff. I'm going to just be going to them and grabbing the thing that we need. Crossover frequency would be omega sub c, as written here, and it would necessarily have to have something in its dependent variable. One of its independent variables would need to be the crossover frequency, or crossover-ish, and it ends up being the case that this is 1 over RC, which is kind of nice, right? So that means when we go to solve for our capacitor value, we will get 1 over 2 pi r fc. That is correct, which means 1 over 2 pi 100 ohm, and then we're going to be using this 1000 hertz thing here. So capacitance should be 1.59 times 10 to the 6, or microfarads. Okay. And by the way, just note, what is crossover frequency? Guess I wanted to say that earlier. That is when voltage in the capacitor is the same as voltage in the resistor. So one of the things we did in one of our exploratory labs is where you would just have this sort of RC circuit, and you would notice that they have most of the time different voltages because they are handling this alternating current differently. Resistance resists in one way, capacitors react resistively in another way, their impedance, so to speak. So, but this, what is a crossover frequency or angular frequency? The omega is angular frequency, and F is frequency. So this is the, what is that crossover frequency, crossover angular frequency, related that way. All right. Number 8. High pass filter with a crossover frequency of 1000 uses a 100 ohm resistor. So we did low, now we're going to do high. Same bit here. Omega C is still going to be 2 pi fc, and this means that our capacitance is going to be same as before, 1 over 2 pi RFC, 2 pi RFC. We'll jam some numbers in here, 1 over 2 pi times all of that stuff, and it's the same stuff. So we're still going to get 1.59 microfarads. Okay. Had to throw an easy one in there. All right, now a circuit. Let's deal with one here. All right, so what are VR, voltage to the resistor and voltage to the capacitor, if EMF frequency, the oscillating voltage, is 10 kilohertz in the circuit below? All right, so see how much room I got here. All right, that's all fine and dandy. So let's let's deal with this here. So I'm going to have some reactance for this capacitor. Seen this formula before, 1 over omega C. And that's going to be 1 over 2 pi. I think we can remember that. And the 10 kilohertz would be 10 times 10 to the third or 10 to the fourth hertz. The capacitance, 80 times 10 to the minus ninth farads. And so we would have a capacitive reactance of about 199 ohms. Okay. And so that's that piece of the puzzle. And current, again, using Ohm's law, but it gets more complicated. Instead of it just being, V equals IR, okay, like we're used to in the old ways. It's going to be a little bit more complicated because we're not dealing with just R. In fact, we're not even dealing with, we're doing two kinds of resistance, two kinds of impedance, the normal resistance that we have in a resistor and the reactance of a capacitor. And so we would be using this formula, kind of old idea for DC stuff, but Ohm's law still applies. If it's an electric circuit, inevitably you can use Ohm's law. But our current that we're looking to solve for is going to be a voltage over resistance or impedance for us. So I'm going to write it this way. Impedance was the Z. So this is really just Ohm's law, where instead of R for resistance, I have Z for impedance, because this is the same as voltage and current still current. Okay, so those are the connections, and you have to make a switch when you're going from DC to AC, or you might just take the kind of the AC world view of voltage is current times impedance, and when you're in a DC circuit, you have resistance as your impedance. That would be possibly a way to organize your thoughts in that regard. Well, in this case, our impedance value is going to be another little Pythagorean-ish thing. It's going to be this sum of the squares of capacitive reactance and resistance. And the reason why that's the case is Z is largely defined as resistance squared plus that. Pretty sure it's capacitive minus inductive. It might be switched, but obviously since we don't have an inductor, that's 0. Hence you get what we have here in that regard. So that's just a little background worth showing. And so 10 volts, if we're talking about at peak, which I think the problem was talking about 10 volts peak, the thing there, our E naught. And there would be an instantaneous voltage that we would just call that big epsilon, that big curvy E thing. But this is our peak, as not initial, so our conventions change as we move through this. And so we just figured out that capacitive reactance was 199. The resistor, I'll just leave the ohms out for that. And what we get is 0.0401 amps. And there you go. That would be like 40 milliamps, 40.1 milliamps if you wanted to kind of do that. And I think, what are VR and VC? So now that I have current in the circuit, I could finish this off, and I just might give myself a little bit extra room here. It's the beauty of one note. So let's get back to black here. So we're going to have VR would equal IR R, if you will. And so you would have our 0.0401 amps times 150 ohms, and that is roughly 6 volts. And VC would be current times its version of resistance. So while this lecture is largely just here's a problem, how do we solve it, we get to make some connections that the textbooks say, but they say it in a way that sometimes isn't the easiest to absorb. And so if you put the numbers in that we already have here, then you're going to get 8 volts. All right, here. So there you go. And that's the weird thing about AC circuits is you get some interesting variations there, and more on that later. All right. I think we might just do 2 in this session. All right, since this is the last one on this, or close to the last one. Did I just skip? Oh, here we go. So, high pass filter, 1.5 microfarad, 100 ohm resistor driven by an AC source with peak voltage of 5. What is the crossover frequency? All right, so we have seen this formula before. Crossover frequency is 1 over 2 pi r c. And so this is not a complicated thing. Now, these 5 mini lectures and or sections of a AC circuits lecture series are a setup to solve some AC circuits like the ones we did for DC circuits. And so there's the groundwork for doing AC circuit solutions a little bit more involved, not as clean, I guess, or straightforward as the DC stuff. I think it's easier than this because there's less, well, there's no variation really because there's nothing oscillating. Anyways, the only changes you have to deal with are node because there's no oscillation otherwise. Anyways, back to the thing here. So 100 ohms for the resistance value, 1.59 times 10 to the minus 9th. No. The minus 6 farads. And that would give me 1,000 hertz. It's almost like it was planned that way. There you go. So that's the crossover frequency, 1,000 hertz. What is the voltage across that resistor when the frequency is half of the crossover frequency? Okay. I guess that was, this should be B instead of, wait a minute, A's, that can't work. What is VR when it's half of that? So this is a little bit more involved. And so let's trot out the formula here. So I'm going to have a voltage, okay, And kind of an interesting formula here that I'm just going to trot out from the textbook that don't need to necessarily develop all of them. So we could do some, equation hunting and pecking and whatnot, and get this all worked out, and then this would obtain another simplification. If you get a common denominator, and so we would have 1 plus 1 over omega squared r squared c squared. And so go back and put that in the book later. It gets to a point where you just, what's the equation for this? And you go and solve for it. And so we can continue this math game, okay? And really, when it all comes down to it, this question is really just a point to a formula that is in terms of frequency, because now we don't have frequency. We got to get a 2 pi f in there and all that jazz. And so what it ends up being in the end is your peak voltage over 1 plus the ratio of this, the square of the ratio of crossover frequency to the whatever frequency you're dealing with. All right. And so if you knew the crossover frequency, which we do is 1,000, and then if you wanted to, when f is fc over 2, so this turns out to be a number. So we're really just dividing our peak voltage by the square root of some number. All right, and so that's a kind of a trivial math maneuver, and you would get some series of voltages that depended on what frequency at whatever f is, or what partition of crossover frequency is. All right, so this is more or less just here's this formula. Okay, it comes from lots of wrangling with fundamental formulas, and you can go do that. That's a pre-calculus level thing, but really this is likely to be the thing that gets used a lot. Okay, unless you're staying in terms of angular frequency, which sometimes you do. All right, low pass filter. Similar situation. In fact, it's the same. In fact, I'm just going to put same as above. There's really not much to be. There's no new thing to do in this. It's literally the same process as the one before it, and so I'm not going to bother with that. I was doing a high-low picking and making up of problems, and then I didn't realize that it's the same thing. So I'm not going to just write the same thing over again. Same as above with the condition of these other values. So I'm going to leave the recording at that, and we will pick up next time with inductors and see if we get all the way to power NAC circuits. But then there'll be probably a single lecture after this that just does a couple of 3, maybe 4 RLC circuits, because that's really the end game, is to be able to solve those circuits in similar fashion as we did with DC circuits, Kirchhoff's laws, and all that jazz. So next time.